So we'll record here. Do the best with this. We're just going to review. As I said, there is a review online. I'm going to go grab it. All right, so we'll continue recording here. I've got some pins now. Other questions for me before we get rolling? So, exam 1, Tuesday. Tuesday, that's June 20th for us. 21st? Oh yeah, Monday is the 20th. Thank you. Thank you. Yes. Tuesday, June 21st, right? Monday is June 20th. That's when the college will observe Juneteenth. So campus will be closed on Monday, but we'll start out on Tuesday. All right. We will probably. What's the best way to say this? Make sure to read syllabus without missing an exam. You email me the day of the exam and say, I'm called into work, I can't come in. All right, that's option B. If you no call, no show an exam, that's a 0. Okay, so just be aware. If you can't make the exam, let me know as soon as you know. If you can let me know 24 hours in advance, we could go with option A. I'll check my email throughout the weekend. I really need more than 24 hours to do it well. But if you give me at least 24 hours, I will work with you. I'll put you in the testing center. I'll have to write you a different version of the test than what everybody else gets. And I'll do my best to make it the same or similar difficulty. The more time I have, the easier that is to do. Inside 24 hours, I just can't do it. Just be a lot more lax about that. It just got overwhelming. 24 hours. That's really not enough. Okay. That's our questions about that. Does that make sense? Okay. Simple things, just be here. Now neither one of us have to worry. I know things happen. If something happens, you can't be here on Tuesday the 21st at class time. Let me know as much in advance as you can. Let me know one way or the other. Even if it's after the fact, you gotta let me know. Okay. You just show up the next day and say, oh, that's a 0. There's got to be a reason you didn't show up, right? Okay. What else here? So we will probably now. One advantage in the summer is since we've got a little more time, we don't have to start like right at noon. We'll start probably around 12:05. We'll start within a few minutes, but since we've got some extra time around the class, then it's not like a regular class where we've only got 75 minutes. We have to get you guys in and out, so the next class can come in. We can be a little more relaxed about it. So we'll probably start about 12:05. Actually, start the exam. Whenever we start, I'll give you 75 minutes from the time we start. So let's plan on probably starting around 12:05. We'll come in, ask, make sure everybody's got. We won't have enough time to answer a lot of questions. I'm not going to be able to look at any examples or anything like that, but just make sure you're kind of settled in. Whenever we get started, it might be 12:03, it might be 12:05. We'll go 75 minutes from that point. I'll put the clock on the board. Okay. All right, what time we're going to stop? You guys have that time? It's summertime. We're moving twice as fast. It's 2 lectures, so we got. I don't like giving an exam and then lecturing after that because I know you guys are spent. It's the summer class. It is how it is, right? So we will have to go ahead and start chapter 4 after. We'll start chapter 4 after the exam. And now, like I said in the website, there in Canvas, or the page that I built in Canvas for you, I did give you 3 videos. It's the very end of chapter 3, equations of state. Watch that between now and the end of the exam Tuesday. Right? So right between now and when you come into the exam, just get those videos watched if you haven't already. Okay? That finishes up chapter 3. That materials, the equations of state are not on this exam, right? But it is, you need that material in place to start tackling chapters 4 and 5. It's just too much to put on one exam to try to put all of chapter 3 on one exam plus 22. Yes, ma'am.
Okay, I had a couple questions. One, how many questions are on the test?
How many questions are on the test? Very good question. 4 questions.
Okay. And also, I saw that you had posted chapter 3 quiz. Is there chapter 1 and 2 as well?
Yeah, no, that's a very good question. There is a chapter 3 quiz available in Canvas. I think I made it due the day of the exam, right? So give you some time. It's the intention there is for that to be completely practice. So what I did is I had some questions where I had to build an online version of exam 1 at some point, and I had that question bank. I just recycled it. So hey, we're going to be an hour late today, so we don't lose the time. So 45 minutes of lecture and then. Yes, ma'am.
Okay, sorry.
That's okay.
Yeah, about the quiz. You did say it was practice. Does that mean it's not for a grade? Or
It is for a grade,
okay.
right? So go ahead and do it.
Is it unlimited? How many
Yes.
times you take it? Okay.
Yes.
Sorry.
Yes. So it is for a grade, right? There's a quiz 3. Quiz 3 available. I would take it at least a time or 2 before you come in and take the exam, but then after you're done with class, we got time, and you got 20 out of 25. You want to try to improve it, that's fine. You can go as many times as you want on it. There are a few versions of each of those questions, so they will recycle each time. Yeah, it's unlimited. As long as you whatever your last score at the time of due is, we'll go with the highest one. Canvas will keep your highest score. Yeah, so I kind of threw that on there, and that'll go in just the generic homework categories, another score. My intentions for that one to be a pretty simple 25 points to get it. Practiced on the property tables and gives you another opportunity to practice the property tables. Okay. Other questions about quiz 3? So chapter 3 quiz.
Well, for quiz 3, the review, is there a separate review?
Review is what we'll do right now.
Okay.
Yeah. So the review is what we're going to do in lecture today. Yeah. So the chapter 3 quiz is just kind of a nice extra review tool available for you. Cool. What else? Awesome. To clarify that, yes. 75 minutes, 4 questions. Okay. Excuse me. Normally, so just to mention, when I grade, kind of like if you read in the chapter 1 homework, a little paragraph in the chapter 1 homework description about a little bit about how I grade. That's how I try to grade all problems. If you show me how to set the problem up correctly, that's worth the bulk of the points, right? That's really what we're after. So this is true throughout the semester. If you find yourself really wrestling with algebra and units, understand you're probably only after the last 5 points out of 25. Okay? I will do everything I can to put, if you show me you've got a very clear path to the solution, you know all the unknowns, and you have as many equations as you have unknowns, I'll do everything I can to get you to 20 out of 25 points. That's a B. So just, like I said, kind of keep that in the back of your mind. If you're like me, you don't want to walk away from a problem when you know how to solve it, right? You want to keep going, you want to finish. I get that. Just understand if you're spending 20 minutes to get to an answer, that's 20 minutes you can go get 20 points on another problem. So just kind of be aware of it. Okay. All right. And the later exams, this one, it's not uncommon. This one will take you most of the time. Some people finish early, some people won't. You don't finish early, it's okay. It's not a race. Understand later, the later exams, most of the time people go to overtime. Just to keep in mind the way I grade. Getting to an answer is much less important than showing me how to get to an answer. Excuse me, sorry. So, kind of alluded to here, content is going to be chapters 1, 2, and then sections 3, 1 through I think 3, 5. Okay, it's going to be up to equations of state. Not including equations of state. So for the 3 videos I've asked you to watch, those are not on this exam, but they will be in the rest of the class. What else? As we mentioned, the syllabus. Resources you can use. You get one sheet of notes. Eight and a half inches by 11 inches. So specify size. You guys are engineers. Don't come in with 8.5 meters by 11 meters. That's too big, right? 8.5 inches by 11 inches. I'm not picky what you put on. If you want to put a bunch of example problems on there, I would suggest you might rethink how you're working your homework problems, make it work some more, but you're welcome to, right? If that's what's going to help you, by all means, that's okay. If you just have some equations on it, that's fine. Right? Probably won't have to put a lot of conversion factors on there if you're familiar with how the inside cover of the back of the book works. There's plenty of conversion factors there, so you should have what you need. Because
Are you okay if I print that off?
Yes. yes, absolutely. So here's the rule. It's an open book exam. So any material from Changle and Bowles text, any version, any material from the Changle and Bowles text, I don't mind you having a printed copy. It's the same thing somebody with a textbook. And even if you have a textbook, I don't mind if you print additional copies. As long as it's from this text, this set of authors, yes, that's fine. Yeah, open book or printed material from this particular book. We talked a little bit about calculators. Right now, I tend to be a little open with them. My general rule is without internet. So as long as sitting on your desk, you cannot access the internet wirelessly. Without internet or PDFs. So if I think you're looking through a solutions manual or something like that on your calculator, we're going to trade it out for one of mine. Questions? Does that make sense? Just a standard, if you're just using a standard calculator, you should be just fine. I'll try to write a little bigger than that next time. Realize that's my limit now. Been a while since I've taught on a document. We'll make it work. Okay, so logistically, that's how the exam works. Okay. I will do everything I can to make every exam logistically work the same way. It'll just be different content and different questions. All right. Then look at content. So are there particular questions you want me to look at? Maybe some examples or some homework you're struggling with? I don't mind doing that. I don't have any examples pre-worked out. What I normally do is I go through kind of an outline of the material, give you kind of a refresh. We've seen the theory, worked some examples in class. Now you've worked some homework. And we come back and we look at the theory one more time, just kind of quickly. And that normally kind of helps solidify things together. But if there are particulars you want to look at, it's free form. We've got the time. I don't mind. Particular, if you think of something, let me know. Stop and say, I've got this example, or what about this homework from this topic from the homework? Give me a problem we can look at. Okay. So we look back at chapter 1 just real quickly here. Dimensions, units, which is going to be, as an engineer in the United States, it's going to be the bane of your existence. Especially in thermal science classes. Thermodynamics is kind of the first of the thermal sciences that most people will take. Many of you will go on to take a fluid mechanics course, and after that, maybe go on to take a heat transfer, or maybe transport phenomena, which is like heat mass and momentum transfer for chemical engineers. These are all what we consider the thermal sciences. And units are units are important in all of engineering, but it really makes some of the problems in thermal sciences a lot more challenging. So when I'm adding or subtracting terms, they have to be in the same units. I can't get them to be in the same units if they're not the same dimensions. If somebody, a student asked me, okay, well, how can I convert BTUs to PSI? Can't, right? Those are different dimensions. That's energy and pressure. All the conversion factors in the world will not get you from PSI to BTUs. As pressure is not energy, and therefore we cannot convert those. So those are different things, but units are used to measure dimensions in a standardized quantity that's easy for us to communicate. We talked about systems. What are the two types of systems we talked about? Two types of systems. What are those? Closed is one. What's the other one? Right, so we don't normally call it, it is an open system, but we don't normally call it that. We call it something else. Control volume. Control volume, absolutely. So control volume is kind of like an open system. Why? What is the difference between the two?
One allows mass to go through and the other just allows energy.
So control volume mass can cross the boundary for control volume. Closed systems, no mass volume. It's just a certain amount of mass contained in some kind of container. For us, it's going to be contained in some kind of container or tank. When your later classes, sometimes that will go on to more general definitions than just that. For our purposes, it's going to be like a tank. The closest is going to be like a tank or a piston, something where the mass is not crossing the boundary. Control volume is just we've established a boundary around some sort of device where mass is going to flow into or out. All right, very good, very, very good. And of course, the boundary is what's going to separate our system from its surroundings. Chapter 4, we'll talk about a lot more about what happens when that boundary moves, the volume of our system changes. There's an energy associated with that we've got to keep track of. And then we talked about properties. Properties are basically dimensions for our system, things we want to measure for our system. So there are three properties that we will typically measure. That is volume, or at least three properties that are easy to measure: volume, pressure, and temperature. Within volume, of course, we talked about the idea of density, which of course is mass per unit volume, which is the reciprocal of specific volume, because specific volume is total volume per unit mass, the reciprocal of density. So we'll use specific volume in this class more than we will density. We'll use density some. We'll really focus on specific volume, especially, and you see that in the property tables in chapter 3. A lot of times we're working with things that can be in the vapor state. It's easier to work with a specific volume of vapor than its density of vapor, because the density is really low. Working with liquid, I probably want to work with the density because the density is high and the specific volumes can be very low because they're reciprocals of each other. We talked about the different temperature scales. Okay, so the change in temperature is going to be the same. A change in Rankine is the same as change in Fahrenheit. Change in Kelvin is the same as a change in Celsius. But Rankine and Kelvin are the absolute scales, and we talked about pressure. Right? And we said in a column of fluid, the pressure will change within a column of fluid, and the pressure change between two locations, 0.1 and 0.2. Change in pressure between two locations, 0.1 and 2, is going to be the density of the fluid between those two locations. Gravitational acceleration locally. And then the change in elevation, in this case, if this is on the left side, if I've got P2 minus P1, here I'm going to say Z1 minus Z2, because here I'm referring to Z as elevation. Z is increasing as we go up. You can write delta P as rho G delta C if you're referring to Z as depth. So as I increase depth, I will increase pressure. This text prefers to use Z to refer to elevation. It took me a little while to get used to it because I actually learned Z as depth in this equation. So it took me a few years teaching it. Once I realized this, it makes sense what this text is doing. They're using Z as elevation in multiple places. So they just say, well, just use Z as elevation. If Z increases, the pressure increases. Okay, that makes sense. Just understood, it's dependent on the weight of the fluid above the location. Right? The weight of the fluid above location, whichever location, is going to cause an increase in pressure. You have multiple fluids. There's a variety of ways we can splice this equation onto others. You can just set up 2 or 3 equations, one for each fluid, splice them together algebraically. Or we mentioned there are some methods you can learn on the internet or some other texts about writing a single equation, add this term, subtract this term. If you're okay learning and memorizing those rules for those methods, that's perfectly fine. If you want to stop by, I can try to point you in the right direction to help you. It's just, I don't like doing that in class because there's just a lot of details that get that mixed up. I have no problems if you want to use the method where they just write a simple equations. If you understand how to do that, that's fine. Okay, that wraps up chapter 1. Again, chapter 1 is focusing on systems and properties. Right? We have to understand dimensions and units to understand properties, because properties are dimensions. We talk about the different properties of a system that we can measure. Right? Then from there we talk about, get into chapter 2. Chapter 2, our focus is on another dimension, another quantity we call energy. So in a physics class, they would have introduced you to forms of mechanical energy, work, kinetic energy, potential energy. These are mechanical types of energy. It's very easy to convert mechanical types of energy to one another. Here, we're going to also introduce a couple of other types of energy that maybe you didn't see in a physics class. We're going to talk about what we consider more of the thermal types of energies. The first law is just simply conservation of energy. The second law is going to be more focused on which type of energy we're dealing with and how can they be impacted. But we'll get to that in chapter 7. Right? We said a general energy, right? So E is when E would be the sum of different types of energy. And so if I've added different types of energy, maybe I'm adding heat and work together. Those are different kinds of energy. So I would just represent it with a general term. And E, we can find E, big E, if I know the mass of my system and I know the specific energy, the energy per unit mass within the system. So we do this a lot. We'll use a lowercase variable for something that's what we call intensive. It doesn't matter how big or small the system is, it's easy to scale up. And if I know how big or small the system is, I can multiply by mass, and that gives me the total energy. We see the same thing back over here with volume. We'll see this with a variety of variables throughout the semester. This is common in the thermal sciences. If something is per unit mass, we'll use the lowercase variable. We're doing the same thing here. Lowercase e is per unit mass, so we use the lowercase variable for the intensity property. Okay. Energy rates. Right? We said if I put a dot above a variable, that means it's a rate. It's being measured per unit time. Something else that's common we do in the thermal sciences. This is E dot. E dot would be the product of M dot and lowercase e. So lowercase e is energy per unit mass. M dot is mass per unit time. Energy per mass times mass per time gives me energy per time. And again, power, the term power is specifically work rate. You know, wouldn't count you wrong if you said heat rate, the rate of heat is power, or any general energy rate is power. Wouldn't count it wrong, but we normally reserve power specifically for a work rate. What else then? And I've mentioned here the M dot, which is the mass flow rate. M dot is mass flow rate. Not the E's. Anybody remember how we find mass flow rate? There's a variety of ways. Yes. Density times volume flow rate. If we look at the dimensions on this, this is mass per unit volume. And the volumetric flow rate, the V dot, again, you put a dot above a variable, that's per unit time. So it's volume per time. So mass per volume times volume per time leaves me with mass per unit. How can I find V dot? If I remember that. So we can go out with a measuring cup and a stopwatch. That works if it's water. Not so good if it's ammonia. That kills us, right? So this is something I can't go out and physically measure. What we can do is if I know the cross-sectional area of the conduit, and I know the average speed at which the fluid flows through that conduit, the product of that area times speed, that's, so there's two lengths here, and this gives me a third length per unit time. That's 3 lengths per time. That's volume per time. So if I take the average speed of the fluid times the cross-sectional area, that gives me the volumetric flow rate, multiply by the density, that gives me mass. And again, have some way of knowing which V you're talking about, because all three of them show up right here, right? Because the reciprocal of density is the specific volume and vice versa. So I can also find this if I know the specific volume by dividing by specific volume instead of multiplying by density. So know which V you're talking about. Let the units be your guide. If it's length per time, that's a speed. Volume per time, that's a V dot. If it's volume per mass, that's a lowercase. All right. So again, chapter 2 is really kind of what we're doing in chapter 2 is introducing to us first law of thermodynamics. First law of thermo simply says that if I take the total energy coming into my system minus the total energy out of my system, that equals the change in the energy of my system. In minus out. Now, you can write the big long equation if you like. That's okay. Right? That's what we're going to do next. Is if we think about our system, we think about what types of energy can come into the system. Well, that can come in 3 forms. There's 3 types of energy that can cross the boundary. That's heat, that's Q. There's work, that's W. And if I've got any mass flowing, that's also going to have its own energy. So these are all the types of energy that can come in. So I'm going to add all those. I'm going to subtract all the types of energy that can go out. And that's the same ones. Q out minus work out minus energy of mass goes out. Now, if my mass is constant, I can, if I say this is equal to, then the change, if my mass is constant, I can factor that out. Right? Now, so it's possible I have as much mass coming in as I have mass going out. I just have to account for the energy. If the mass happens to be constant, then I just have m times all the specific energy changes. Well, what types of energy can the system have? Right? The system can have internal energy, so that could change. It can have kinetic energy, that's v squared. It's v2 squared minus v1 squared, both over 2. And it can have potential energy. Just about ran out of room. Probably should have moved to the next line. Normally, I don't like writing in the margins of engineering paper, but I'm just trying to squeeze one line. Use the ends, subtract the outs, that equals the change. I would suggest having that on your equation sheet, obviously, right? But what I'm trying to preach to you here is don't think about this as just one equation with lots of terms. Think about this as a concept. Think about this as, again, you're conserving energy. That means the in minus the out has to change. And then you can kind of break it up into pieces. You don't have to remember each term arbitrarily. You can remember, all right, well, what are the types of energy that can go in or out? Heat, work, mass. So I add those terms in, subtract those terms away. And that equals the types of energy that can change. There's 3 types of energy that can change. It's internal, kinetic, potential. Again, the way we're learning the brain works is if the more, at least for most of us, the more connections you can have to arbitrary bits of knowledge, the easier it is to remember. So that's what I'm saying. Break it down into its pieces. Don't just try to memorize one equation. All right. So we talked about each of these terms a little bit. We said for us, in chapter 2, that the heat is it's either going to be what we're looking for, or it's something that's given to us, right? Or the problem's probably expecting us to assume it's negligible in chapter 2. Now, chapter 4 we can't make, and beyond. Chapter 4 and beyond, we won't be able to say, well, we don't have the heat. We're just not going to worry about it. Right? We can do that a little bit in chapter 2. Sometimes we can't do that so much in chapter 4, right? And beyond. But the good news is we're going to get better and better at working with this equation, simplifying it as we go. The work we talked about, there's some different ways we can find work terms. There's electrical work. The work can just be given to us. It might be some force that we just integrate over distances. We have a handful of tools for finding work terms. But the first law also, that's the only unknown in the first law equation. I can solve for one of the unknown works just fine. Again, it's only one equation. So it means I need to be able to find or know which of these I can neglect, get it down to where I've only got one unknown, or have another equation I can use. The internal energy. So in chapter 2, it's kind of like that in terms of how we deal with it is similar to how we deal with heat. It's either something that's given to us or it's what we're looking for. We might be looking for the change in internal energy. Or they might just tell us it's negligible. We might assume it's negligible. The temperature difference is one of the biggest drivers of that. But as we've seen in chapter 3, other properties influence it as well. Okay. So the goal is, here in chapter 2, we introduce to you the first law and say, here's why we need to understand how we find u of things. And when we go to chapter 3 and we spend all this time talking about how we use property tables, if we haven't shown you, hey, you need those u values to solve this equation, sometimes it's kind of lost as to why are we going to all this trouble to learn how to use these silly property tables. You need those property tables to find properties like u based on properties we can measure, like pressure, temperature, volume. So it's a process. We're kind of building as we go, right? And we're getting up to now where we're going to really start working on some pretty interesting problems, but let's make sure we got a good handle on chapter 2. So there's another concept then that shows up in chapter 2. We don't see it too much then after chapter 2 for a while. There's this idea of efficiency. We use a symbol eta to refer to efficiency. That's common in most engineering. Okay. conceptually, they like us to think about this as output over input, they being the authors of this particular text. I'm not the biggest fan of this idea. It works most of the time, so I can understand why they like preaching it's always output over input. It's not, I don't think that's fair or a good idea to say it's always output over input. Most devices we work with, we're trying to produce some sort of desired output, and that's going to be less than the required input. So it's a pretty good model that works most of the time. Conceptually, you want to think about it as what do you want or what do you desire divided by what do you have to do to get it. It's also should always be expected smaller value divided by the expected larger value. Why is that? Well, as a rule, efficiency is a number between 0 and 100%. Going to be unitless. It's a ratio, so that means it needs to have the same units in the numerator and the denominator. So BTUs over BTUs, watts over watts, horsepower over horsepower. Just depends on what you're measuring. You're measuring power over input, heat input. Are you measuring energy over some other energy? Are you measuring distance over distance? Efficiency can be used for any type of thing. It doesn't have to just be limited to thermodynamics. It can be, you can take a variety of things. But a true efficiency, it's an actual efficiency, it's going to be the same quantity or same dimensions on top and bottom. We get them in the same units. And then when we take the ratio, we get this unitless quantity between 0 and 100%. That's a true efficiency. There are other ways we can measure performance in a similar fashion. We'll see some of that in chapter 6. Aren't actually what we would call efficiencies, but it works with the same concept. Two piles of paper here. I'm trying to keep them straight. All right. Page 4. Okay. What else we got here? Questions so far? Adiabatic, what's that mean? No heat transfer. Okay. Adiabatic, term we need to understand it. It just means no heat transfer. I'll tell you it's adiabatic. You can immediately set your Q equal to 0. It might also tell you, if they tell you it's well insulated, they're telling you the same thing. Those are the common things that they'll tell you in this particular text. I've seen some other texts will tell you some slightly different things. I want you to make the same assumption. If they tell you it's adiabatic, they tell you it's well insulated, or they just simply tell you neglect heat transfer. So it's saying all the same thing. Adiabatic means a process during which there's no heat transfer. What else then? By the way, on the chapter 2, I've got those of you who submitted chapter 2 homework as of last night. I graded the problems out of the text. I'm going to go back and see. I think I had some solutions for the additional problems in my office. I didn't have them at home, so I want to grab those if I have them. If not, one way or the other, I'll get those graded back to you guys tonight. Okay. Apologize I didn't get those done, but that is between me getting sick and having a dozen middle schoolers running around in a camp, I'm happy to be here today. Thank you guys. I really do. I can't tell you. I really do appreciate you guys being patient. And like I said, it should be normal the rest of the summer. All right. That is chapter 2. Okay, that's very rapid fire chapters 1 and 2. We'll talk about chapter 3 just a little bit. Okay. How you doing on chapter 3? Brand new. Chipping away at it. Okay, keep chipping away at it. We've mentioned this a few times. It's a learning. Like you have to go through that process and learn how that process works. I can go through it 500 times with you. You have to be able to do it on your own. Right? So that takes practice. So I'm not kidding when I say, have that list of Steve's steps going through property tables. Have that next to you, if that helps you for your first 100 times you use property tables. And after that, you'll start becoming second nature. Not exaggerate 100 times. We throughout the rest of the semester, we will work with water in R134. We will need to be able to find U values, water in R134 throughout the semester. That's property tables. Chapter 5, we're going to need H values. We'll talk about why when we get there. Chapter 7, we're going to need U values and then S values, the entropy values, and we find those the exact same way. So that's, like I say, practice that. That's the reason I set the chapter 3 quiz up for you guys. Give you some additional practice. Hopefully it helps. It wasn't intentionally, I was not intending to be extra burdensome, just give you an additional tool. All right, what else then? So that brings us then to chapter 3.
Chapter 2, we look at the next one on the energy rate. So that equals the mass flow rate times. Yes.
Yeah, so it's just the E dot just specifies that it's just energy per unit time. So the common way we'll get there is if I know some energy per unit mass multiplied by the rate at which mass is flowing. That'll give me the rate at which energy is flowing by mass. That's the most common way we'll see that. So in a control volume, I'll have material flowing through it constantly, and I may not know the exact amount of time over which that occurs. So all I can do is just look at the rate at which it's occurring. And we'll see that. Thermo's kind of the first place where we really start seeing where you can work the problem a variety of ways. You can work it per unit mass, work it per unit time, depending on what's given to you. Sometimes we have to work it one way, sometimes we have to work it another way. I know that's new for us, but we kind of introduced that concept. What else? Cool. Let's continue on. We'll talk about chapter 3 now. Let's refresh that a little bit. That should be somewhat fresh, but let's hit that again. Seeing it, especially because it is so fresh, hitting it again does not hurt. So let's just start here. We'll just say using property tables. And I might not get this exactly right. Oh, right. I might not get this exactly the way I drew it on the board the other day, or exactly how I listened to the videos. There might be a difference between how it was in the videos and how I put it on the board. But the general process is about the same. Number one, identify your substance. Anytime you're looking for property tables, I'm going to say, or determine properties. Anytime I hit a point in the problem where I need to know a property for my system. Anytime I need to know some property, whether it's a U value, whether it's an S value, whether it's a T value. The first question becomes, what's my substance? What is my substance? What is my system made of? And then what tools do I have to try to quantify those properties for that substance? For us, it's going to be water in R134 right now. Chapter 4 and beyond, it might be some ideal gas as well. And those will be the main substances we'll deal with. It's water, R134, and typically air is going to be our ideal gas of choice for the most part. But it could be nitrogen or oxygen, carbon dioxide, something like that. So those are the common substances we're going to deal with. We'll touch just a little bit on solids and liquids. Those are pretty simple tools for those. But number one, what substance am I working with? And that's going to determine what path I'm going forward with. Step 2 then is identify known properties. Now, for water in R134 tables, I say R134. It's R134A. There's technically an A at the end of it. I rarely say it. I try to write it, but I rarely say it. For water in R134, I need at least two. I need at least two properties. In a rare circumstance, I might need three. We can talk about that. I'm not going to intentionally give that to you. I need at least two properties. Now, one property could be the phase. They can tell me I've got saturated liquid or saturated liquid. That would be sufficient. I would need to know another property, know what pressure, temperature that's in. Step 3 would be to determine state. Where do you live on the PVT surface, the three-dimensional PVT surface, which we're not going to plot it on the surface, but what it does mean is we need to know which table and which row. That's really what we're saying here. So if I'm using property tables, which table am I using and which row within that table are my values going to come from? Or it could be, as we'll see, it could be rows. One row. Then that's interpolate between. Right? So some things to mention here is you have to watch your units. And it's going to require you to determine what we call the phase. Solid, liquid, gas, vapor, where am I? On the spectrum. Because the tables are broken up depending on the phase. Step 4 is record desired properties. Go through and willy-nilly record all the properties. You can. I'm not going to. I'm going to go back to my problem. So here in chapter 3, we're just, the goal is just to learn to use the property tables. We're going to go back to chapter 4. Chapter 4 is going to give us, we're going to have this problem. We're going to take this first law equation. We're going to simplify it. We're going to have one, maybe two of these energies on the left-hand side. Probably not going to have kinetic potential energy. So probably heat minus work is going to equal m delta U for chapter 4 problem. So I'm going to use the properties that are given about my system to determine the U values from the tables and use those to find either the heat or the work, whichever one's not known. That's how this is going to look moving forward. So which properties do you record? Well, you need to look at the rest of your problem and see which ones you need. Do you need the volume? Do you need the internal energy? Later on, do you need the entropy? Now, as we've seen, as we work through these, I've kind of determine the phase is just a nice, simple little sub point there. It's where most of your effort's going to be. Determining the phase is one that's going to take you some of the most practice. So we break that out into its own section. Determine the phase. It's not just as simple as just go do it. I mean, it is once you get used to it. There are two main scenarios. Hope if I could write that. Right. So as we said earlier, you need at least two properties. You need at least two properties. That's going to come in one of two flavors, so to speak. Right. Given P or T and V, U, H, or S. This is the first scenario. The first scenario is given P or V, one of these two, and then one of these fours. These are your two properties. It doesn't matter which combination. There's what, 8 different possible combinations there, okay? Doesn't matter which of those 8 possible combinations you have, it looks the same way, roughly. You can put P or T, whichever one you're given, on the y-axis, V, U, H, or S on the x-axis, And you just arbitrarily can draw this diagram. And what you do is, given your P or T value, you go look up the values for saturated liquid and saturated vapor. And that tells you where the edge of the saturation dome is at that given pressure or temperature. And then given your other value here, whether it's VUH or S, go look up the liquid and vapor values for that property, VUH or S, and then compare yours to these two and see where it puts you. If it puts you in between, you're in a saturated mix. If it puts you out here, you're in a superheated vapor. To the right, you're in a compressed liquid. Now, my preference is to draw it out. Okay, we can write this in words easy enough. It comes in the form of like 5 if-then statements, right? If at given P or T, I'm just going to say V, and that could be V, U, H, or S. The rules are the same, right? If at the given P, your V is less than V sub F, you have what we call a compressed liquid. So then if at, and again, what I'm writing down here is just this in words. So if the words help you, fine. If not, I'm going to write them one time and I'm not going to write them again. Okay. Well, it's worthwhile to write them one time. It's worthwhile to process information multiple ways. So it's okay to write them out. We talk about it, right? But this is probably the only time I'm going to write them out. So if at the given pressure or temperature, your V value is equal to V sub F, that tells us we have saturated liquid. That liquid is right at the point of boiling. It's literally boiling liquid. If I add any more energy to it, some of it's going to vaporize. Okay. Well, if at the given pressure or temperature, your V value then is between these two. So I'm going to say V sub F is less than V is less than V sub G. Okay. Your V value is between these two limits. That puts you in the dome range. If this is your scenario, you have a saturated mix. A saturated mix. So how do we do that? Well, we need to find the quality. The X value is the quality. We'll call it quality. This is the portion in the vapor phase. Okay, how much of it? It's somewhere between a vapor and a liquid. How much is a vapor? How much is liquid? We're gonna have to figure that out. How do we figure that out? Well, given the V value you have, subtract from it the V value for saturated liquid. And then divide that by the V value for saturated vapor and subtract the value for saturated liquid. So it's V minus V sub F over VG minus V sub F. And I can do the same thing for all 4 properties. U minus U sub F. So this is also equal to U minus U sub F divided by UFG. That UFG value is the difference between UG and UF. So you can manually take UG minus UF. The saturated vapor value is always larger than the saturated liquid. This is always the saturated vapor value, no matter which of the properties it is. It's always larger than the liquid. So there's always this difference on the bottom, right? And again, this UFG is just UG minus UF already done for you if you want to use it. Same thing for H, the enthalpy. Same thing for the entropy, S minus S sub F over SFG. So once I find the quality with one of those four properties, I can use that quality, that X value, then to find the other four properties. Okay? Again, remember, quality is between 0 and 1. What's the quality of its saturated liquid? If it's saturated liquid, how much is in the vapor phase? 0. Right? Saturated liquid, a shorthand way you can write that is you can say quality is equal to 0. You can see that here. If I plug in V sub F here, this becomes 0, X is 0. We only use the quality if I'm talking about saturated something. Okay? I don't use the quality unless I'm talking about saturated something. It's not saturated, I don't care. It's nonsense. If it's saturated, anything, I can use the quality value. If it's a mix, quality between 0 and 1. If it's saturated liquid, it'll be 0. Next scenario is if at the given pressure or temperature, your V value is equal to V sub G. This is a saturated vapor. I don't normally write that out. I just normally write X is equal to 1. Again, the X tells me it's saturated. 1 tells me it's 100% the vapor phase. That tells me it's saturated vapor. So as I said, there's about 5 if-then statements. There's 4. Here's the 5th one. If at the given pressure or temperature, you have a V value that is then greater than V sub G, this puts you in the superheated vapor region. Okay. And then we just go to the superheated tables. They are rather extensive. You might fall between rows, just interpolate between rows. I do that. You might fall between pressure blocks. You can interpolate between pressure blocks. Pressure might be in between 2 different blocks. Just interpolate between 2 different columns. If you need help with that, stop by. It's interpolation. The math is pretty simple, but conceptually, I understand it's a bit of a challenge once you kind of start seeing it. After we do it a little bit, it starts getting a bit easier. Questions so far? This is one scenario. Again, my preference is the diagram because while this is thorough and this is very good, you can see how I don't think this is efficient myself. I'm a picture person, right? If I see it, it makes more sense to me. There's nothing wrong with this. This is perfectly good. And there's detail here I don't have here, right? I haven't talked about the quality. It's important. This is what it looks like in words. Okay. So what am I doing here? Well, I'm saying, all right, well, given my pressure or temperature, go find these values and compare mine to these values. And that tells me where I am on the diagram. And that's what I'm saying here. It's given pressure, temperature, find your value. How does it compare to the other limits? And that's how we determine the phase. That's one scenario. That covers all 8 of these combinations. The other scenario is a little simpler. Only one possible combination of that. Okay. Determining the phase, part 2. That is the scenario where I'm given pressure and temperature. Again, I think the diagram is a nice, simple place to start. We can write it out in words. I'm happy to do that. I like to draw a table when I do that. But let's talk about this second. Put P on the y-axis, T on the x-axis. Just draw a curve arbitrarily out there. Concave up curve, half u basically. What I like to do is take the given pressure and go look up the saturated temperature. That's the boiling temperature. And if your temperature that you have, right, is greater than the saturated temperature, that puts you over here in the superheated vapor region. If my temperature is less than the saturated temperature, that puts me on this side of the curve, which is the compressed liquid region. An easy one to think about is I've got water here, right? So as long as this water at 1 atmosphere, right, 101 kilopascals, my saturated temperature for that water is going to be about 100 degrees Celsius. So if I have water that is at 1 atmosphere and it's above 100 degrees Celsius, that puts me over here on this side of that curve. That's maybe superheated vapor region. If my water is at a temperature less than 100 degrees Celsius, this is probably, I don't know, it's not to see. It's probably 40, 50, 40 degrees Fahrenheit. So probably in the teens in Celsius. That's going to put me over here because 100 is here and I'm back here. So it puts me in the liquid region. Now, if we put this out in words, which is not a bad idea, again, nice way to process information multiple ways. What I like to do with this is I like to build a table. I'm going to build basically a 3x3 table, 3 rows, 3 columns. We'll draw 3 columns across, and we'll close the bottom off when we get it filled in. So what's this look like in words? Well, if I've got compressed liquid, right? So what that looks like is at the pressure, your temperature is less than the saturated temperature. And the saturated temperature is a boiling temperature. So at the given pressure, your temperature is less than the saturated temperature. That's a compressed liquid. Now you can look at it the other direction. I prefer to, given the pressure, go look at the saturated temperature. That's what I prefer to do. You can, given the temperature, go look up the saturated pressure, but it flips. The direction here flips, okay? What that means is, so at the given temperature, what happens is if I have more pressure than the saturated pressure, so if my pressure is greater than the saturated pressure. Now, what I do in my head to wrap around how I think about that. So the saturated pressure is the minimum pressure at this temperature to keep the molecules in the liquid phase. If I have more pressure than that, then it's going to push those molecules even harder together and force them to stay in the liquid phase. Okay? So this is basically the saturated pressure is kind of the minimum pressure required to maintain liquid at that given temperature. If I have more than that, I'm going to maintain liquid just fine. It's not as natural to think about probably, but that's how I wrestle that around in my head. Maybe that helps you a little bit. So the next scenario then is at the given pressure, my temperature is equal to the saturated temperature. My phase is saturated. It's on the curve. Now here's the problem with that. I don't know where it's at. All I know is that I'm somewhere between here and here on the saturated dome, right? From this side, because here I'm looking at the edge of the saturated dome, I don't know how far, which way on the saturated dome. I don't know where it is in here. It's somewhere in here. If I have pressure, at the given pressure, I go look up the saturated temperature and it matches. I have saturated something. I need a third property. This is the only scenario where 2 properties does not work. Third property. You're somewhere between a liquid and a vapor. We don't know enough information to tell you that. Not something I would intentionally give you, wouldn't give you on a test, I wouldn't intentionally give it on a homework. Right? You would have to, that's a scenario where, okay, the problem is literally impossible, you just have to explain why it's impossible. I don't have enough information to determine the phase, therefore I can't give you the V value, the U value, whatever it is I need to solve the problem because I don't know how much vapor and liquid we have. Again, not something I would give to you, but it's just something to be aware of. Same thing here. T at the given T, pressure is equal to the saturated pressure. It's just not enough information. We just know we're on the curve. We just don't know how far into or out of the page we are. Okay. So third row then down here. That's the superheated vapor row. So how do we know we're at a superheated vapor? Well, the simple one is, again, the way I like to do it is at the given pressure, I go look up the temperature. If my temperature has exceeded the boiling temperature, the saturated temperature, that puts me over here in the superheated vapor region. Now you can go at the given temperature, go look up the saturated pressure. Okay. So if I have a temperature, go look up the saturated pressure at that given temperature. Then if my pressure is lower than that, that drops me down in here to the superheated vapor region. It puts me below the curve, the lower pressure, right? And again, the way I wrestle that in my head is I think about, again, the saturated pressure. The saturated pressure is the minimum pressure required to maintain liquid. If I have less pressure than the minimum required to maintain liquid, the molecules are not being pushed together as hard, so they're allowed to fly off. They're allowed to escape each other. That's how I wrestle. Hopefully that helps. Questions there? Hopefully that helps a little bit solidify, seeing that just another way. I'll solidify that a little bit. Again, we're going to use that throughout the semester. Okay, last couple of things here. For compressed liquid. Right, so I've got compressed liquid for water in R134. We use V, U, H, S, saturated liquid at a given temperature. If you know you have compressed liquid, you ignore the pressure, essentially. Unless it's like a really high pressure. We're not even going to worry about it. We're just going to assume temperature is the driving factor for a liquid. We'll look up saturated liquid values at the given temperature. And that'll give you just a fine estimate. It's an estimate, but it's a pretty darn good estimate. Good for 2 significant figures almost always, probably good for 3. Last little bit to talk about here. 7. If your value falls between rows, we'll just call them rows A and B. So if I'm looking for a value between 2 rows, between a couple of values, how do I do that? Well, I'm going to construct a line mathematically. So basically, you've got data points for point A, so let's say x minus XA, and point B, so it's on the bottom here, so it's x minus XA on top, XB minus XA on bottom. So basically, I'm constructing a line mathematically between points A and B. So y minus YA divided by YB minus YA. So the last example, we were between temperature values. So we said, well, use the temperature values here for X. We're looking for the Y value. In that case, it was the V value, the specific volume. It could be the internal energy, entropy, any of the other properties. If I know I'm between two temperatures, I know my U value is going to be between the U values for those respective temperatures. Use this to figure out how far in between these two this value is. Solve it right now. So algebra wise, they're pretty simple. It does take a little practice learning how to say those. What else? Questions? For me? It's a solid 75 minutes of rapid fire review of 3 chapters. Tell my voice is getting close, but I'm happy to talk. If you guys have questions, I'm happy to answer. I'm happy giving you some extra time. You got the chapter 3 quiz to work on. It's a nice place to start. Start on the homework. If you haven't got the chapter 1 and 2 homework done, get those in. I'll finish grading chapter 2 homework this evening at the latest. Okay. All right, guys. That's what I got today. Have a good rest of your week. Have a good long weekend. I'll see you Tuesday. We'll take the exam. And we'll start chapter 4. See you guys then.